A historic moment, NASA confirms Voyager 2 has sent back a signal that every scientist quietly feared. The heliosphere, our sun's protective bubble, has torn open. This is no longer a simulation, no longer a distant theory. It's real data from the only human-made object drifting beyond the solar system, Voyager 2. The call from interstellar space. The signal crackled through NASA's Deep Space Network in Pasadena, California. Weak but unmistakable. Voyager 2, a battered golden spacecraft launched in 1977, had crossed a boundary scientists once believed would hold forever. At more than 140 astronomical units from the Sun, Voyager 2 detected something shocking: a sudden rupture in the heliospheric boundary. For decades, it was assumed that this boundary, the heliopause, would gradually thin as solar wind waned. But Voyager recorded something else entirely: a sharp spike in cosmic ray intensity paired with a dramatic drop in solar wind pressure. A tear, a breach. For the first time, the Sun's cosmic shield had failed, and Voyager 2 was there to see it. What is the heliosphere, and why it matters? The heliosphere is not visible to the eye, but it shields all life on Earth. It's a vast bubble of charged particles, plasma, emitted by the Sun. This plasma pushes outward, forming a protective cocoon that deflects cosmic rays from the rest of the galaxy. For billions of years, this bubble has acted like an invisible force field. It stretches beyond Pluto, encasing every planet in our solar system. Without it, we'd be bombarded by high-energy radiation that could tear apart DNA and fry electronics. The outermost edge, the heliopause, was once thought to be a stable boundary. Now, Voyager 2 has shown us otherwise. In this invisible struggle between the Sun and the galaxy, the heliosphere is our front line. Its strength fluctuates with the solar cycle, growing during solar maximum, weakening at solar minimum. But no one expected a breach this abrupt. The moment of rupture. Since crossing the heliopause in 2018, Voyager 2 had been quietly measuring interstellar plasma, density, temperature, and particle velocity. For years, the data showed minor fluctuations. Nothing alarming. Then it happened. A sudden surge of high-energy particles overwhelmed the spacecraft's detectors. Solar wind pressure dropped sharply. Engineers thought it might be an error, a glitch from a probe decades past its prime. But days of analysis confirmed the readings. The heliosphere had been pierced. The event was so abrupt, so violent, it overturned every prediction. No model had prepared scientists for such a collapse. What had once been a firm cosmic barrier had become permeable. Galactic forces had found a way in. The question now, was this a one-time anomaly or the beginning of a new phase? Consequences for space exploration. This breach has monumental implications. Humanity has long dreamed of venturing beyond Mars into deep space. But now, the radiation environment we thought we understood has changed. Spacecraft shielding, previously deemed sufficient, may no longer be enough. Designs for Mars missions, asteroid bases, or interstellar travel will have to be re-evaluated. We may now require thicker bulkheads, magnetic shielding systems, or even entirely new protective technologies to survive the galactic radiation that is now surging inward. New mission proposals must account for increased radiation flux. Communication networks may require redundancy. Crewed missions may need real-time particle storm warnings and active shielding. Long-term habitation in space has become more dangerous than previously imagined. This discovery doesn't only complicate our ambition, it questions our preparedness. Effects on planets and Earth itself. The breach doesn't just affect empty space, it affects everything. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are now more exposed. Their atmospheres are being bombarded by cosmic rays with greater intensity. This could alter their magnetic fields, affect atmospheric chemistry, and generate auroras unlike anything we've seen. Radiation interactions with their magnetic belts could produce exotic ions and particle storms. Their moons, many of which are considered potential habitats for life, may now experience increased radiation as well. What this means for microbial habitability beneath the ice of Europa or Enceladus remains unknown. But even Earth is not immune. Our planet's magnetosphere works in tandem with the heliosphere. With the Sun's bubble weakened, more galactic particles can slip through. Radiation exposure on commercial flights, especially over polar routes, may increase. Satellite electronics could experience more frequent bit flips and failures. Astronauts aboard the ISS might need stronger shielding. Cosmic radiation affects not only machines but biology. Airline crews, frequent flyers, and future space tourists may face subtle but cumulative health risks. The calm that space engineers once designed around may no longer exist. A new scientific frontier, Voyager 2 has handed us not just a discovery, but a mystery. What caused the breach? Was it a one-time shock, or does it happen cyclically during solar minimums? The implications ripple outward. Planetary scientists must now consider how solar shielding varies over time. Climate scientists may need to revise models to account for galactic ray surges during quiet solar years. Astrophysicists are beginning to ask, do other stars experience this too? Are other planetary systems occasionally left vulnerable by a thinning stellar shield? The heliosphere is not unique. Every star generates its own bubble, called an astrosphere. If such ruptures are common, they could reshape our assumptions about habitability across the galaxy. Exoplanets once considered safe may be regularly exposed to radiation bursts. Life in the universe could be rarer or more resilient than we believed. Voyager 2's breach could be a Rosetta Stone for astrobiology. Humanity responds, or should. Inside mission control, emotions run high. Voyager 2, built in the 1970s, has outlived its creators. With failing power and aging instruments, it's still sending back data no other machine can provide. But the warning is clear. The solar system is more fragile than we believed. Policymakers are now facing tough questions. Do we invest in more resilient spacecraft? Do we pause human deep space missions? Do we launch new probes to map the breach before Voyager 2 goes silent forever? Meanwhile, engineers race to adapt. AI-powered fault-tolerant systems, radiation-hardened hardware, optical communication that can cut through charged plasma clouds. New ideas are being tested. Plasma deflectors, superconducting shields, spacecraft cloaked in magnetic fields. Institutions are updating curricula. Aerospace students now study dynamic heliospheres and galactic turbulence. Climate models now include cosmic flux variations. Space weather has become interstellar, the legacy of a golden ambassador. Voyager 2 was never supposed to last this long. Designed for a 5-year tour of the outer planets, it is now our only eye beyond the solar system. Its golden record still spins. A message to alien civilizations, or perhaps to ourselves, of what humanity is and what we dared to dream. Its final act may be its most important. It has shown us that the sun's shield is not invincible, that the galaxy presses in, that the stars do not always shelter their children. And in that revelation, Voyager 2 has given us a new challenge: to prepare, to explore, and to survive in a universe more dangerous and more wondrous than we ever imagined. The bubble has broken. The stars are closer now. Are we ready?